Hello. In this video, I'm going to explain problem 12 from the 2013 F=ma contest. In this problem, we have a spherical shell of mass m and radius r, completely filled with frictionless fluid, also of mass m. So here we have m, r, and then the fluid inside is also mass m. And it's released from rest, and it rolls without slipping down an incline with an angle of theta. And we're asked to find the acceleration of the shell down the incline just after it's released. And we're given the formulas for the moment of inertia of a solid sphere and a hollow sphere. Now, these are formulas that are worth memorizing because I've seen problems where they're not given and you would be expected to know them. But here they've been nice and they've given it. Just a small note before we begin this problem. All right, so first important observation is that the fluid will not rotate, only the shell will. And basically, because this is a frictionless fluid, the fluid will ultimately just stay as it is because there's nothing. Basically, ultimately, when you have an object rolling down an incline, the friction makes it roll because that's what exerts the torque about the center of mass. But for the frictionless fluid, there's nothing to exert that torque, and so it will not rotate. And so this is actually something interesting that you can see in an interesting way. If you take a water bottle and you fill it with water, or so let's start with so if you take a bottle filled with water versus if you freeze that bottle and have it filled with ice, then this will roll down much faster, or roll down incline much faster, and this will be slower. And the reason is that the water will not rotate, and so the water will not take up any of the potential energy as rotational kinetic energy, whereas the ice will rotate with the bottle, and so as a result, it will use up some of the potential energy that the bottle, or that as the bottle loses potential energy by rolling down the ramp, it gains kinetic energy, but some of that kinetic energy will be used up by the rotating ice, and so it will ultimately accelerate down the ramp slower. So this is an interesting way, sort of a real-life physical example. So now let's go to the problem. Here we have an angle theta. Here we have our sphere. Now, the sphere has two forces on it in the direction of the incline. So one is acting on the center, and that is a total of 2 mg sine theta. Remember that both the shell and the fluid have masses of m individually, so the total mass is 2m. And it's sine theta because that is just the direction, just the component of gravity parallel to the incline. And then we have a frictional force that acts right here, F frictional. All right. So now we need to compute what this will be, or what this frictional force will be, in order to determine how quickly this shell filled with fluid will accelerate downward. So let A be the acceleration, and we'll let alpha be the angular acceleration. So we know that due to rolling without slipping, which means that the distance that the disk, or that the shell covers, is the same as the distance that it covers on the ground, or whatever surface it's rolling on, will be the same as the distance covered on the sphere itself, and that means that in this case that the acceleration will just be equal to the angular acceleration multiplied by r. And now we can ask, what are these two quantities? Well, we know that 2ma will equal 2mg sine theta minus the frictional force by Newton's second law. And we know that alpha will be, we know that the moment of inertia, which for the solid sphere, remember that's just what matters, is that 2/3 mr squared. That's the moment of inertia of the sphere, of the shell, and that's what will actually rotate. Alpha will equal the frictional force, and so that is Ff times the radius, and that is the torque. And so now if we solve for this first equation, what we will see is that 2/3 mr alpha is equal to Ff, just dividing by r, and then r alpha is equal to a, and so what we get is Ff is equal to 2/3 ma, and so now we can plug that back into here. So we get 2ma is equal to 2 mg sine theta minus 2/3 ma, and so then moving this to the other side, we'll get 8/3 ma is 2 mg sine theta, and then of course we can cancel m's, and ultimately what we get is that a is equal to 3/4 g sine theta. And so now, if we go back, we can see that 3/4 g sine theta is the correct answer. Another way to see this would be to ask, what fraction of the kinetic energy would be used up, would be translational, and what would be rotational. And so if we have the sphere moving at some speed, let's say it's rotating at omega, then the speed will be omega times r. And so the translational kinetic energy would be 1/2 times the total mass is 2m times omega r squared, because that's the velocity. And so what we would get is 2m omega squared r squared. And now the rotational kinetic energy will be 1/2 times the moment of inertia. So that will be 2/3 mr squared, because it's just the part that's rotating, so just the shell, and then multiplied by omega squared. So what we would get is 1/3 sorry, this is not 2m omega squared, that's just a silly mistake on my part. It is just m omega squared r squared, because these two canceled out. And here we get 1/3 m omega squared r squared. And you can see that the rotational energy, kinetic energy, is 1/4 of the total kinetic energy, and the translational is 3/4. And so what this means is that when let's say you have an object rolling, this object rolling down versus an object sliding down a certain height, then basically this one will have 3/4 the translational kinetic energy as this object. And remember, this one would accelerate at g sine theta. And since it has, and remember the kinematics equation vf squared minus vi squared is equal to 2ax. In this case, it starts at rest, so vf squared would just be 2ax. And remember, Vf squared is just proportional to the translational kinetic energy. And so if this has 3/4 as much of the translational kinetic energy, it has 3/4 as much of the v squared, meaning that the acceleration must also be 3/4 as much. And this is another way of seeing that. And so those are just two different ways of getting the same result, A equals 3/4 g sine theta. All right, I hope that was helpful, and thank you for watching.